Alright, so book 1, prop 4 is kind of where things start taking off a little bit. It's a really interesting proposition for actually a couple of reasons. So, reasons that I think are mostly philosophical. So my plan is to kind of walk through the proof, which there really is nothing for me to do in terms of like writing. So what I'm going to do is I'm going to read the Heath translation and kind of like translate it into, you know, modern math language, the way that we might intuitively think about things today. And then I want to just say one or two things briefly about why I find it interesting. So here's prop 4. It's all of this up here. Today we call this the side angle side proposition, which basically, again, in modern parlance says that if a side, an angle, and a side in that order, so two sides with the angle in between them, if you have two triangles where they both have that same side angle side, then prop 4 says those triangles are congruent. But how does Euclid say it? Well, he didn't say it so concisely. He said if two triangles have the two sides equal to the two sides respectively, and have the angles contained by the equal straight lines equal, they will also have the base equal to the base, the triangle will be equal to the triangle, and the remaining angles will be equal to the remaining angles respectively, namely those which the equal sides subtend. Yeah, so it's kind of wordy. It's super duper wordy. One thing that I think is sort of interesting in here is that in addition to him basically saying, yeah, if the side angle side condition is met, not only are all of the sides of both of the triangles equal, and all of the angles between equal sides are also equal, he says also the triangles themselves are equal, which I think is interesting because it's like having the sides the same and the angles the same respectively to us means that the triangles are equal, but it's still something that he felt the need to kind of explicitly state, that just because all the sides are respectively equal and all of the angles are respectively equal, he felt that wasn't enough to just say, okay, the triangles are equal, like those are two separate things. At least that's how I interpret some parts of this, the business about the triangle will be equal to the triangle. Okay, so let's run through this proof. So he says, let's suppose that we have ABC, triangle ABC, and DEF are the two triangles. He says, having the two sides AB, AC equal to the two sides DE, DF respectively, namely AB to DE and AC to DF, and the angle BAC equal to the angle EDF. So I guess just some things I can mark up here in terms of like the modern notation. So we have AB is equal to DE. Looks a little bit fuzzy, I don't know. Maybe it's just my view. AB is equal to DE. What else do we have? AC is equal to DF. And then angle BAC, so in other words, what we might sort of shorthand as angle A, is equal to angle EDF, or angle D. So side angle side. And this is, again, this is more modern notation using these kind of, to my knowledge, I don't know when this historically came about, but I don't think that this was common for Euclid in Euclid's time to be using like these dashes to indicate like congruent sides. So, alright. So he says, alright, and then he kind of restates everything. So he says, if this is the case, then here's everything that follows, and here's how he proves it. He says, for if the triangle ABC be applied to the triangle DEF, and if the point A be placed on the point D and the straight line AB on DE, then the point B will also coincide with E because AB is equal to DE. So he uses something that hasn't been mentioned at all previously in the elements. It's not mentioned in the definitions or in the postulates or common notions. It's not any of the previous propositions. He uses something that we today call superposition, which is basically like, imagine if I could pick up triangle ABC and move it over and place it on top of D. In particular, place it so that A coincides exactly with D, and we lie the side AB along the side DE. So like take this thing, place it so that A is on top of D, and then start placing AB down along DE. He claims, well, since that's the case, since we know that AB, the length of AB, is equal to the length of DE, if we were to lay AB across DE in the exact same direction, we would find that B coincides with E. So if A is laying on D and we lay it down, then B ends up laying exactly on top of E. And then he goes more. He says again, AB coinciding with DE, the straight line, AC will also coincide with DF because the angle BAC is equal to the angle EDF. So he's saying that as we've taken ABC, we've laid down AB. You can think of the triangle kind of like at an angle like this, right? And then we're going to sort of like lay it down. And he's saying that as you lay it down, since these two angles are the exact same, this side, AC, is going to fall along the line DF, and moreover, since AC is equal to D, I guess this is the part that I didn't read, but he says, hence the point C will also coincide with the point F, because AC is again equal to DF. So he's claiming that as AC is being laid down along DF, the point C will coincide exactly with the point F. And then he says, but B also coincided with E, hence the base BC will coincide with the base EF and will be equal to it. And to me, that's the first place. I mean, aside from the superposition, it's kind of like, all right, the superposition, I'll give you that, Euclid. That's fine. You haven't really rigorously defined any of that. It's not formal, but I'll give it to you. To me, this is the first place where I go, prove it. How do you know? Just because these sides, like, it's begging the question, because he's basically saying, like, yeah, well, since these sides are the same with the angle in between them, yeah, for sure it's going to end up being the case that these lines are the same. And the kind of unspoken axiom that Euclid is using here, sort of a postulate that he's invoking, but he hasn't actually said it, is the idea that 2 points uniquely determine a line. That is to say, it's not possible for 2 distinct straight lines to pass through the two of the same points. He doesn't say that. They kind of just like took that as an intuitive, obvious truth. But it is something that today, if you are, if you're kind of trained in mathematical thought and rigor, that should be a place where you go, wait a second now, like, that seems like it requires a little bit of justification. And I don't know if that's exactly why David Hilbert ended up creating his own axiomatization, I don't know, of geometry. But it does seem likely because, what is it, his very first incidence axiom says exactly that between any 2 points lies a unique line. And with that extra axiom, this does end up being true, assuming that you allow the superposition argument, which again is kind of a shaky premise. Right, so that's kind of something that's sort of interesting there. And then he just kind of goes on to restate, like, yeah, and this is going to prove everything else, because we've proved now, at this point, that BC is equal to EF. And then next he says, and that's from Common Notion 4. Let's see, what is Common Notion 4? I had better look back and remind myself of it. Common Notion 4 says... Oh, okay, so I guess Common Notion 4 does kind of introduce the idea of the uniqueness, because Common Notion 4 says things which coincide with one another are equal to one another. So I guess that kind of does take care of the uniqueness of that line. He goes on to say, thus the whole triangle ABC will coincide with the whole triangle DEF and will be equal to it. Again, Common Notion 4. and the remaining angles will also coincide with the remaining angles and will be equal to them, the angle ABC to the angle DEF and the angle ACB to the angle DFE. Therefore, we are done. So, right, kind of interesting stuff. One thing that I find really interesting, and I didn't write this out, so you would have had to have heard me sort of when I was going through the justifications, but the only justifications that Euclid uses in this proposition is common notion 4. So it's kind of interesting to me because the whole point of the elements is to start off with these definitions, postulates, common notions, and then to build up this entire book with, kind of each proposition building on each other. And up to this point, before Prop 4, Prop 1, Prop 2, Prop 3, they did that. Prop 1 was just based off of the axioms that were set forth. Prop 2 just pretty much used the axioms in Proposition 1. Prop 3 used the axioms in Proposition 2, but then Proposition 4 doesn't use any of the previous propositions, and it only uses one common notion, which is interesting because it means that Proposition 4 falls out directly from Euclid's system of axioms. It's standalone. Right, and I think that's most of the reason that I think that's interesting is, for me, just kind of from the teaching standpoint of things, because I immediately just sort of think well, if you didn't need any of the previous propositions in order to do Proposition 4, why did you wait until Proposition 4 before you stated this? Why not state this as Proposition 1, and then the new Proposition 2 would be our original Proposition 1, and then build things up sort of that way. It's kind of strange that it's okay, Prop 1, and then Prop 2 builds on Prop 1, and then Prop 3 builds on Prop 2, which built on Prop 1, and then there's Prop 4, which stands alone. Me personally, I kind of have two theories. One, probably the more realistic one, is that, and this is one of the reasons that I really admire Euclid, is more than him being sort of what I might strictly call a mathematician, I think that he was more of a math teacher. He was just an excellent math teacher, and the elements kind of points in that direction, because it's if you want to teach somebody geometry, the way that he did it is exactly the way you want to do it, where you start off with these intuitive notions and then you build up everything from there, rather than just throwing students in and then, kind of making them figure things out on their own. He does this build up. And so my sort of thought, my speculation, is the reason that he chose to put Prop 4 where he did, this is just my speculation, is that he felt he wanted the elements to have this feel of building blocks that were constantly building up something greater. And this one, Prop 4, compared to Prop 1, because Prop 1 also was proven just using the common notions and the postulates and the definitions. But Prop 1 is much more intuitive. Prop 4 starts using something that is not exactly the most intuitive mathematical idea. I think that it's sort of there's a layer of abstraction involved in proving Prop 4 over what was involved with proving Prop 1. And so that's kind of my feeling, is that Euclid wanted to kind of build some confidence in the student and build some confidence that these are all just kind of building on each other, and that we're not going to do any of the hand wavy oh, poof, and then here some things happen and then now we've proven what we wanted to prove, because that's a little bit how Prop 4 feels to me. This superposition argument isn't really stated anywhere. There's just some shaky logic that feels like it's going on. Anyways, yeah, I feel like that might be, partly I think that, what am I trying to say? Mostly I feel that Prop 4 appears where it is because Euclid was a really outstanding teacher, and he understood that Prop 4 is sort of the earliest that you can introduce this proposition, so that students aren't immediately feeling like the rug has been pulled out. beneath them. But it also could be the case that he wanted to hide the fact that, he wanted to really build up the elements in a way where it felt like, yeah, every single proposition in here ties back to the previous propositions, and Prop 4 kind of doesn't fit that mold, and so he sort of secretly shuffled it in at Prop 4, which is maybe both the earliest and the latest that he could do it in order to build up the elements. Anyway, just some speculation, nice and quick proof, and it turns out to be one of the really, really important ones as we build up the elements.